The usual power reactor is a very concentrated source of power, producing electricity to sustain about 1 million people. This can readily be seen from the numbers I provided. 100 reactors, more or less, provide 20% of electrical power for a United States of 300 million people. So 500 such reactors would provide all of the power for 300 million people. So a single reactor would empower about 0.6 million U.S. residents. In our discussion of world energy futures, we'll note the enormous disparity between the developed world and the less developed world, even the rapidly developing countries of India and China. But now I want to characterize the reactor as a node in a system of supply of fuel, delivery of electricity, and creation of spent nuclear fuel. The 25-ton annual reload of uranium fuel to a power reactor could conceptually fit easily in a single railway freight car. Similarly, the spent fuel from the reactor, which is 1 kilogram lighter, according to Einstein, 1 kilogram out of 25,000 kilograms, because of the mass that has been absolutely converted not only into electrical energy of 1 million kilowatts for 8,000 hours, but also into the heat that constitutes twice as much energy and is dissipated typically to cooling water in a neighboring lake or river. Following this a bit farther, the 25 tons of uranium at about 4% U-235 is derived from about 8 times that much, 200 tons of natural uranium. That itself, with a uranium ore concentration of 0.1%, corresponds to about 200,000 tons of ore mined in Australia, Canada, Russia, or one of the other sources of crude uranium, an article of commerce known as yellow cake. In contrast, a coal-fired plant requires about 3 million tons of coal to be delivered each year to the power plant, and results in almost 10 million tons of carbon dioxide, CO2, ejected into the atmosphere each year. It's clear that the transport of nuclear fuel is far less a burden than the transport of coal, as was evidenced by the impact of unusual snowstorms in China on the transport of coal to fuel the electrical generating and industrial plants of China in January 2008. Indeed, the disposition of ash from conventional coal-fired plants is also a problem, constituting as much as 10% of the 3 million ton annual feed. At this point, we resort to a more compact notation in which 1 million is represented as M, or mega, so the 3 million tons is 3 megatons. And the ash requires perhaps 0.3 megatons of transport capacity annually for each coal-fired power plant. No matter what is done with the ash, much of it made into concrete, it does require transport of enormous magnitude compared with the transport of fresh or spent nuclear fuel. But the ash from a coal-fired plant is inert. Once having cooled from the fiery temperature of the boiler to room temperature, it is like any other material, although it may contain toxic elements to some extent. The ash from a nuclear plant has nothing in common with that. At 25 tons per year, it is perhaps 10,000 times less massive or voluminous than the ash from a coal-fired plant, but the comparison stops there. Fresh fuel for a normal reactor consists of thin-walled metal tubes, about the size of this pen, but very long, filled with small pellets of uranium oxide ceramic containing about 4% fissile U-235 and 96% U-238. Spent fuel, removed after 4 years in the reactor, has about 4% fission products, 0.9% residual U-235, 1% plutonium, about 65% fissile plutonium, and about 0.1% non-plutonium, so-called transuranic elements. Plutonium-239 is formed by non-fission capture of neutrons on uranium-238. The uranium-235 in spent fuel would seem to be valuable, present in larger concentration than in natural uranium, which has only 0.7%. But in fact, uranium from spent fuel sells for a lower price than does natural uranium in view of the contamination of uranium-236 that is present and a relatively small amount of uranium-234. The major problems, though, with the spent nuclear fuel are in the fission products, which are highly radioactive, with the longest life dominant components, strontium-90 and cesium-137, each coincidentally of half-life about 30 years. The strontium-90 is a pure beta emitter, so requires very little shielding to be transported. But cesium-137 has an intense gamma ray, and a tiny fraction of the annual production is indeed used as an artificial source of very high-energy X-rays for medical diagnosis or treatment. Together with the other fission products, these 30-year half-life elements produce heat, and as a result, a fuel element downloaded from a nuclear reactor, even after 2 years of cooling in a deep pool of water at the reactor, if lifted into the air by a hoist or crane, glows red hot within minutes because of heat produced by the continuing decay of the fission products. About 10% of the mass of fission products have radioactive lifetimes exceeding 1 million years. Despite the self-heating from radioactive decay, the spent fuel after 2 or 5 years of cooling at the reactor in the French model can safely be transported in heavy-walled casks for ultimate disposition in a mined underground repository, or in the case of France and soon to be Japan, to a reprocessing plant where the uranium, plutonium, and residual components of the spent fuel are separated. Being less valuable than natural uranium, the recovered uranium is often simply stored with little radioactivity involved. The plutonium is separated in that model in order to be recycled into mixed oxide, so-called MOX fuel, in which typically 5% plutonium is diluted with uranium left over from the enrichment process, depleted uranium, to form fuel elements that are essentially equivalent to the enriched uranium elements used in reactors. The fission products, intensely radioactive and containing, as presently practiced, the transuranics beyond plutonium, are vitrified, formed into glass, with appropriate glass-forming material and cast into stainless steel containers about my size, welded, closed, and cleaned. These are then stored with airflow to cool them until they can be deposited into a mined geologic repository. Although this process is advertised in France and Japan as essential because these nations are without fossil fuel resources or native supplies of uranium, the maximum saving of fresh uranium is 20%, and the saving is achieved at a cost equivalent to $700 or so per kilogram of natural uranium. Traditionally, uranium has been available at a cost of $30 per kilogram, although it has spiked to $100 per kilogram recently. The present reactor fleet consists primarily of so-called light water reactors, with a small component of heavy water reactors and graphite water reactors. I showed you 7 of the current 300 full-size reactors. The next slide sketches a light water reactor, like LWR, in which uranium is fissioned in a thick pressure vessel containing about 100 tons of low-enriched uranium, producing 3,000 megawatts of heat, converted at about 30% efficiency in a turbine to 1,000 megawatts of electrical output, 1 million kilowatts of electrical output. I want to consider expanding the present 20% of electrical Thank you. I want to consider expanding the present 20% of electrical power from nuclear energy to essentially all of electrical power, and to satisfy half of the remaining energy needs, leaving aside only remote locations and transport. In an expanding population, with the standard of living that we hope will increase rapidly. About 2,000 reactors would, in principle, provide all of the electrical power now used in the world, and 6,000 would satisfy all current energy needs. So 9,000 current generation reactors would provide a substantial portion of the energy needs of the world of 2050. Let's see.